Hello dear learners. In this lecture, we will try to understand some processes, the photochemical processes in the Earth's ionosphere. We will define what are the basic general processes and in how many different ways these processes can exist in each of the ionospheric layers. So, this discussion is entirely about the photochemistry of D, E, F1 and F2 layers. Right. So, this is the basic structure of the Earth's ionosphere. You just remember basic features, electron density being written on the x axis in per centimeter cube, and this is the altitude in kilometers. Right. So, this is height 250 or 300 kilometers is the peak of F2 layer, approximately corresponding to 10 to the power of 12 electrons per meter cube. Okay. Remember, this is the D layer, this E layer clear infection point, and F1 and F2. Okay. Now, we will see what are the different types of ions which will exist, compensating the total strength of negative charge density. Okay. In how many ways the ionosphere is coupled? We've already seen what and all are the sources of ionization in the Earth's ionosphere. So, in this, what we are seeing is different processes, many phenomena which occur in the Earth's atmosphere at different altitudes. Okay. So, most of them are listed here, and where do these phenomena occur is indicated with the help of these two boxes. So, E region, F1 region and lower thermosphere is the place where auroral precipitation, joule dissipation, solar extreme ultraviolet radiation, absorption, the plasmaspheric downflow, the scattered radiation, etc., are prominent in this region. Whereas, if you come to the lowermost altitudes of the ionosphere, it is coupled with tides and gravity waves from the surface. Okay. And from the top, it is coupled with meteoric ablation, ultraviolet radiation, X radiation, very energetic particle precipitation, etc. So, this region is dense and this region is not so dense or rare. And these are the principal ionization processes in the Earth's ionosphere. So, you see this, all the different types of ions which can exist and what are the processes which result in the formation of these ions and how do these ions exchange or reorganize to form different types of ions. Okay. So, principal ionization processes are nitrogen with a photon releasing an electron will form N2 plus. So, this is a molecular ion, which means the energy that is required must be of the order of X-rays or ultraviolet radiation, right. And then another principal ionization process is a photon interacting with an atomic oxygen or a molecular oxygen. It is dissociating and then forming NO plus ion. This N2 plus ion can combine with O2 plus, result in the formation of exchange of charge and giving O2 plus ion, and sometimes it can combine with O, leading to the dissociation of molecule and subsequently forming an ionic state which is NO plus, right. So, these are the principal ions, and this N2 plus ion can recombine dissociatively with an electron, resulting in the formation of two neutral nitrogen atoms, or this NO plus, which is also a molecular ion, can combine with an electron by the means of a process which is called as dissociative recombination process, okay, resulting in the formation of neutral atoms. This molecular ion again can recombine with an electron, resulting in the formation of dissociative recombination with two oxygen atoms. Okay. And within these four ions, several cross correlations can happen because of the availability of species, right. So, in essence, we have the major ionic species are N2 plus, NO plus, O plus and O2 plus. Okay. This is a molecular ion. So, this goes with dissociative recombination. What is dissociative recombination? So, N2 plus directly coming in contact with an electron will lead to the dissociation of this molecule, which is N plus N. Where did the electron go? This electron has compensated this positive charge on the ion. So, this is called as the dissociative recombination reaction or process or whatever. Now, most important aspect about this dissociative recombination reaction is that it is very, very fast. Okay. The characteristic lifetime or the reaction rate coefficient for this is very, very fast. So, it will happen instantaneously. The other ion O plus, so O plus plus electron can also give O plus H nu. Now, this is the total positive ion density here. The total positive ion density here is entirely equal to only the electron density, right. So, you have to distribute the electron density according to the number of positive ion species which are present. So, let us say in the topmost altitudes of the Earth's ionosphere, the most important or the most dominant positive ion is O plus. Okay. So, here this O plus can only recombine with certain number of electrons. How many number of electrons? Equal to the number of O plus ions. So, let us say if there are 10 O plus ions, it can only take care of 10 electrons, right. And if there are, so if there are more molecular ions, more electrons will recombine, right. But they can only take care of certain number of electrons equal to their strength, right. So, which means that there are some processes which are very, very fast, which will take care of the entire population of electrons, but there are some other processes which will take time. So, this taking time is what goes on during the entire night, and the ionospheric layers at some altitudes will be present during the night time as well. So, what have we learned? We have learned what are the principal ionization processes and in how many different ways the ionosphere is coupled to the atmosphere above and atmosphere below. So, what are the forcing mechanisms? These are all forcing mechanisms which can have influence on the ionosphere. So, auroral precipitation, for example, auroral precipitation will bring in a lot of charged species, energetic electrons, energetic protons, energetic ions into the ionosphere. And so, ultraviolet radiation, X radiation is of course ionizing the neutral species. In addition to this, these charged species will also ionize, will also result in the formation of aurora, etc. Joule dissipation. So, when the currents are passing, the medium gets heated up. The exchange of energy, the loss of energy in terms of heating can be called as the Joule dissipation, solar UV, extreme ultraviolet radiation. So, these are the forcing mechanisms which can have influence on the ionosphere, and tides and gravity waves are the forcing from the surface or from the lower atmosphere, right. And then we have principal ionization processes. Now, what are the processes? Those are the principal ions and how they exchange the charge, how they recombine, etc. Generic principal ionization production processes, these are generic. I mean, we are not referring to something specific, let us say oxygen or nitrogen. Let us say an atom with a photon, this is called as the photo ionization process. It is simple, the most straightforward, right. Xy plus H nu, a molecule, Xy is a molecule, okay. Xy plus H nu gives you Xy plus. So, this is directly producing a molecular ion, it is not even dissociating, and then an electron, a free electron which is produced. This is the process of ionization. Now, here you have positive molecular ion and then Xy plus plus electron. So, here electron is getting attached to the neutral species. So, this here it is a negative ion, you see, negative molecular ion. So, like I said earlier, somewhere I have said that total negative charge species density is entirely by electron. Spare a very small percentage of negative ions which exist primarily in the lowermost part of the ionosphere. And again, an electron getting attached to a neutral atom and producing a negative ion. So, here in this case, if you want to equate the total, if you want to write the photochemical equilibrium, charge equilibrium, you have to write x plus xy plus is equals to x minus. Let us say I write the densities here. I put a square bracket, which means the number of this, okay, is equals to x minus plus xy minus plus electron, okay. This is all 100%. So, to a broader estimate, so this can be up to let us say 5 to 10% and then plus 90%. So, this is how the charge equilibrium is achieved, okay. So, principal ionization processes or generic production mechanism, okay. Now, ionospheric chemical reactions, what are these processes called as? Radiative recombination. The earlier slide showed us in which ways, in how many different ways, electrons and ions can be produced. Because these species are energetic and unstable, they will try to recombine and go back to the neutral state, which is a stable state. So, what are those? Radiative recombination. So, it is a recombination in which radiation is emitted, right. So, what happens in this? A positive ion simply interacts or recombines with an electron, producing a neutral atom plus radiation. The energy difference has to be emitted out, which will be H nu, right. So, this process is called as radiative recombination. The recombination reaction in which radiation is produced is called as a radiative recombination reaction, right. Now, look at this. This process is slow. The rate coefficients are of the order of 10 to the power of minus 12 centimeter cube second. Okay, this is the speed. So, this radiative recombination reaction can happen at a speed of 10 to the power of 12 recombinations, let us say, per second in a centimeter cube volume. This is the radiative recombination. So, it is already said it is a slow process. Dissociative recombination reaction, what happens in this? A molecular positive ion comes in contact with an electron, and this interaction leads to the dissociation of this molecule and subsequent loss of positive charge state. So, here we have X, Y. So, if you have NO plus H nu, this can give you N plus O. This is a very fast reaction. So, rate coefficients of the order of 10 to the power of minus 7 centimeter cube per second. So, this is 10 to the power of minus 12. So, this is a very small number in comparison to 10 to the power of minus 7, right. So, this is the speed at which this recombination reaction can take care of the charged species. So, if you leave this process within this particular amount of time, the charged species will be lost. Charge exchange, this is a different type of reaction. In charge exchange, what is happening is there is no there is no total loss of charge state. Rather, charge is being exchanged from one molecule to another molecule. Wx plus is the original positive ion. It comes in contact with another molecule Yz, and this charge gets transferred to the other molecule. So, Wx now becomes neutral, Yz becomes positively charged. So, this is moderately fast. This is something lying exactly in between these two, radiative recombination and dissociative recombination. It is moderately fast. Rate coefficients are of the order of 10 to the power of minus 10 centimeter cube per second. So, these numbers are the ones that you have to remember these numbers. So, various aspects, let us say the heights, the densities, the peak altitudes, these recombination rate coefficients, all these numbers are not only for just showing. So, they mean a lot. You may have to do some calculations based on these numbers, and it is very important for you to remember these numbers. Only then the understanding will be complete. Okay. So, charge exchange is this simple reaction in which charge is being exchanged from one molecule to another molecule, and then you have ion atom rearrangement or ion atom interchange. So, in this process, a positive ion comes in contact with a neutral molecule, and this there is a rearrangement of molecular configuration. So, YZ is now broken up, and let us say this becomes a neutral XY and Z plus. The rate at which this reaction can happen depends on the strength of this YZ, the bonding between Y and Z. So, if it is very strong, the process will become slower, and vice versa, right. So, now these are the principal recombination processes in which or through which the ionosphere can disappear. Okay. Now, just to have a clear handshake, you have the processes in which electrons and ions are produced, and you have these processes in which electrons and ions are lost. Okay. And some of these are slow and some of these are fast. Okay. Now, extending these generic processes into the entirety of the variety of species which can exist in the thermosphere ionosphere system, this is all what you get. So, photoionization can happen with an oxygen atom, an oxygen molecule, nitrogen molecule, resulting in the formation of molecular as well as atomic ions and equal number of electrons. So, collisional excitation, what happens if the electron is very, very energetic, it collides with a neutral atom, producing an electron in addition to the original one and a positive ion. Charge exchange is simply putting charge, removing charge from one ion to and keeping it on another neutral species. So, these are all different types of processes, chemical processes in the thermosphere ionosphere system. Right. Now, there is a lot of mass transfer, or there is a lot of movement of the fluid from one point to another point. So, now in the ionosphere, we write a generalized continuity equation. Continuity equation is simply referring to the conservation of mass. Okay, mass, or we write an equation in which the rate of change of mass is equal to 0, then we have the continuity equation. If it is not 0, then you should be able to tell where it has gone, how much has been produced and how much has been lost. If these two are not the same, then where is the difference going? Is it remaining inside the system, or is it if the difference is larger, is the system generating some additional mass in addition to the production and loss, etc. Right. So, generalized continuity equation encompasses all those aspects. So, the generalized continuity equation can be written as dNE by dt is equals to Q minus L minus delta E. So, you are referring, let us say, we are talking about a small control volume, or what do you say, a small cube, that is it, which is in the ionosphere. Okay. The rate at which the number of electrons within this control volume changing with respect to time becomes equal to the rate at which they are produced inside. Solar radiation is falling, let us say. The rate at which they are produced and the rate at which they are lost by recombination, it should be minus, right. So, when something is produced and how much of it is being taken out in terms of recombination, L, and if there is a transport of fluid from one place to another place, then additional charge density may also have been brought into the volume, which is del E, which is referring to the transport term, which is basically the advection term. If you remember the discussion about continuity equation in fluid dynamics, or even our discussions about control volumes, you should be knowing all these things, that how the advection term is responsible when you are following the motion. Okay. So, the advection term gives the effects of transport, right. Now, if alpha is the recombination coefficient, now this is where it becomes slightly interesting. So, if alpha is the recombination coefficient, alpha refers to the rate at which electrons and ions are recombining, okay, is the rate. Alpha has to tell you how many electrons are lost per unit time, right, is also a rate, okay. So, then the loss can be dE by dt, the rate of change of electrons with respect to time. Now, we are referring to the loss, the recombination, right. So, that is why we have put a minus. So, which means L is equals to minus dE by dt. L is the rate at which electrons are lost, right. So, we can write it as alpha times E and P plus. Alpha is the recombination coefficient, right. So, this is alpha times the electron density times the ion density. So, at photochemical equilibrium, we always know the total positive charge density P plus is always equal to the electron density. So, P plus can again be written as alpha. So, which means minus alpha times E, or which is equals to minus alpha E square. So, loss term is equals to minus alpha times E square. So, we can substitute that into this term and write the continuity equation as dNE by dt is equals to Q plus alpha E square minus del NE. Okay. Now, let us look at the meaning or consequence of this recombination coefficients, some being larger, some being smaller. Okay. So, the recombination time, the characteristic time within which the electron density will vanish from the ionosphere. So, the rates at which the electron density would disappear will decide the existence of ionospheric layer at a particular time, or the rate at which electron density would disappear, the recombination time will decide the extent up to which the electron density can persist in the ionosphere, beyond which the charged species or the charged state of matter is simply lost. Right. So, how do you calculate the rate? You know the rate alpha, recombination rate. How do you calculate the respective time period associated with that rate? This is a simple calculation. In your chemistry lessons, you may have already learned about these things. So, time constant is alpha times E taken an inverse, or 1 by alpha E. So, alpha is in the units of 10 to the power of, let us say, 10 to the power of minus 12 centimeter cube per second, right. So, alpha times E. So, that characteristic time constant is 1 by alpha times E, that is it. You go back to this slide where we have discussed the rates of recombination. So, take this alpha 1 as 10 to the power of minus 12 and alpha 2, which is the other process, alpha 2 as 10 to the power of minus 7 what centimeter cube second inverse, right. So, these two are rates. So, why am I not taking these two rates? Because these two processes, of course, they exist, they happen, but they are not very frequent. They are very, their percentage of contribution is very small. Most of it is either radiative recombination or dissociative recombination. Dissociative recombination happens first. So, it will neutralize the entire molecules. What is remaining has to be taken care by atomic ions and respective their counterparts of electrons, right. So, taking these two things, example, we can take electron density to be 10 to the power of 12 per meter cube. This is per meter cube, okay. So, I have also converted the radiative recombination also into the units of meter cube and per second, right. So, why have I taken 10 to the power of 12? 10 to the power of 12 corresponds to the F2 layer, not any random number. It's just not random number. So, for F2, Ne becomes 10 to the power of 12 electrons per unit volume. Okay, so you are multiplying this with rate constant, right, which is meter cube second inverse. You are taking an inverse, right. So, what will remain? You will get something in the units of time actually, right. So, this is electrons, of course, this is a number, right. So, per meter cube will get cancelled. So, whatever is 1 by second inverse, which is in the units of seconds. So, here the calculation is simple, 10 to the power of 12 into 10 to the power of minus 18 taken inverse, right. So, this is 10 to the power of 6 seconds, which process is this? Radiative recombination. So, this is 10 to the power of 6 seconds, right. And the second one is, this is the first one, the same electron density, 10 to the power of 12 electrons being taken care by the dissociative recombination with a characteristic lifetime of 10 to the power of minus 13 and taken an inverse, right. So, which is 10 to the power of minus 1 taken an inverse. This is 10 seconds and this is with 10 to the power of 6 seconds and this is 10 seconds, right. Now, you see 10 to the power of 6 seconds corresponds to, if you divide it with 10 to the power of 6 seconds divide with 60, you will get in minutes, then again you will divide with 60, you will get in hours, okay, and then you can convert into into days. So, at least at this point of time, let us say 1 divided by, right. So, it is still a lot of hours, right. So, reasonably speaking, if radiative recombination alone is to take care of the entire electron density, it will take several hours, several hundreds of hours, and dissociative recombination will take few seconds, that is it. So, that is why I say that dissociative recombination is a very fast process and radiative recombination is a very slow process. So, dissociative recombination will happen initially, it will remove all the electrons and equal number of molecular ions, and then what will remain? The atomic ions will remain and their counterparts. So, that is why ionosphere will not exist in the D region and F1 region in the night time. Only the E region and F2 region will persist throughout the night. So, we will conclude this discussion here, and in the next lecture we will learn about the specific aspects about D, E, F1 and F2. So far what we have discussed are valid for the entirety of the ionosphere. Of course, we have defined processes which are slow, which are fast, specific processes, but we have not yet seen where these processes will be dominant, in which altitude these processes will be dominant, etc. So, we will continue in our next discussion and we will try to address those questions.